Welcome everybody. It's a really great honor to have Giuseppe and Longzhu here. And Giuseppe and Longzhu are my friends from Yale and Cambridge. So it's really great to have them here. So Giuseppe Amatuli is a research scientist in geocomputation and spatial science at the School of the Environment, Yale University. So Giuseppe is also a forest scientist and spatial modeler with expertise in computer science. So he deals with high resolution data on a daily basis in the context of a complex and model modeling using standalone implementation process under Linux environment. So he uses a lot of open source programming language and software like Grass, R, Python, Orc, Bash, QGIS, OpenEV, and so on to accomplish a lot for data processing and cluster processing, and keeping always in mind the ecological aspect of the research study. And another presenter today is Longzhu. So Longzhu is a research associate at Cambridge's Department of Zoology. So Longzhu is also affiliated with the university's Center for Data-Driven Discovery. So Longzhu's research interests reside in tackling challenging interdisciplinary problems with modeling approaches. So both of them have very rich experiences in geocomputation and machine learning. I also have learned a lot while I was at Yale doing my postdoc. So I think this might be a very good opportunity for us to learn each other, and many of the tools that they use are actually used much less in China. So it's really a good opportunity for us to learn from them. So without further ado, let's give the time to Giuseppe and Longzhu. Let's get started.
Thanks, Shadow. Can you start recording, please?
Yeah, I've already started.
So it's recording.
Yeah, I'm recording on my own computers. Then I can share with you all if you like.
Okay, perfect. Yeah. Thank you very much. Okay, Longzhu, you can start. I will be.
All right. Okay. First of all, thank you so much for the introduction, and for everyone who make it today. It was kind of a little help gymnastics to have to do, but gladly we got together. So,
recording in progress.
Okay, I just got a notice. Oh, okay, it's fine. So continue. I will begin. Just start with my presentation. I think it's already late now in China. Thanks for everyone for putting up with us. I'll try to go with a little entertainment and interesting discussion if that's possible. All right. So you guys can see my screen, right?
Yeah.
Fantastic. So today's talk is going to be a joint effort between me and Giuseppe to talk about intelligent modeling in the time and space, especially combine the geocomputation and machine learning for environmental applications. So I will kick off for the beginning part, basically at high level talking about the human effort to quest for intelligence. Then I will turn over to Giuseppe to discuss more details about applications. Primarily, now it's very early in the United States. Giuseppe needs a coffee to wake up or something. So I will begin with a little bit about myself. Shall I already kindly introduce myself? I just want to give you a little more detailed picture of myself. So I was trained as a modeler. My background is in quantum chemistry. Of course, that's not only enough for me to satisfy my curiosity. So after my graduation, I migrated into the domain of machine learning. I have applied this technique in a variety of domains, and also met Giuseppe at Yale University. Then I moved to Cambridge, started working on mathematical biology. Of course, large-scale spatial computational modeling and machine learning is my great passion, and that's probably most relevant to this talk. I'm a scientific programmer. I studied with C language, quite fluent with R, Python, and many other popular tools. I'm also a Unix enthusiast. Have experience with all the Linux system and many BSD varieties. So some of you may have known me already. For those who don't know, actually I'm currently residing in Cambridge. So it's a small town in south central part of England. And this is a city quite interesting because a lot of great events in the history has occurred here. So here there's few figures are very representative. I'm going to talk through so that I have a visual tour of this small city, very interesting. The first one is a book published in 1859. That's the Origin of Species, when Darwin started pick up and talk about where the human came from. Actually, there's a little typo in the book that actually has been viewed as a symbol for the authenticity of the original version. Now it's available in the Cambridge Library. And this is a pub, as you probably already guessed. It's kind of lighted and very nice looking. But that's not actually the key point. The key is this little two figure here. If you can see, with a little effort, the two persons are actually Watson and Crick. So what happened here is, back in those days, these two guys were too noisy in the biology department in Cambridge. The people have to drove them away and end up in the pub, start discussing about the science. And that's actually at this table where they discovered the structure of double helix DNA. So a lot of exciting stories. Apart from the science, there's also nice, animals and lives. It's a city full of bounty and beauty. But by the way, this photo was taken in the city center, not in the suburbs. So that's not only what Cambridge offered. Cambridge also offered a lot in great relevance to intelligence. That's going to be the topic I'm going into. So I have to push the time back into 1930s. Of course, I wasn't there, but that's not important. More importantly, someone else is there. It's Alan Turing. So he actually has been credited as the father for computer science and also the beginning quest for intelligence. Back in those days, people were kind of interested in a decision problem posed by Hilbert in the end of the 19th century. His idea is basically, whether mathematical questions can be tackled through a series of recipes. Basically saying, okay, is 1 plus 1 equal to 2, or 17 a prime number, something like that. And it stirs some puzzles, and people trying to attack it from different angles. Alan came to the idea saying, okay, if that's the case, how about we make a machine? We just make a machine called Turing machine. It's pretty much a machine designed to accepting recipes and generating solutions. If this machine can be made, then apparently this answer is true. If this machine is not possible, certainly it defies the question. Then he constructs this kind of Turing machine for a scenario to really tackle this answer this question. The setup is basically, instead of the Turing asking questions posed by human beings, he asked whether the Turing machine can answer questions posed by another Turing machine. And in the end, basically, problem boiled down to whether the machine can stop to get an answer or continue working forever. And he has proved the halting problem, which is kind of a converted version of decision problem, is not solvable. So in conclusion, the Hilbert question got settled. And people kind of thinking, yeah, computers is pretty much just machines following instructions. Actually, if you look at computers today, no matter you do programming or just use spreadsheet, Excel, Word document, it's more or less you give instructions to let computer do some service for you. But by 1940s, people start getting deeper to look into logics in the computer. And there's some analogy between the high complexity of computer logic and the human brain. Then people start questioning whether the machine can think like human beings. And once again, Turing came out trying to address this question. He came up with a genius design, so-called Turing test. Basically, he's trying to show, how do we know if a machine can think or not? And let's do a test. Basically, the test does is a bunch of questions through a defined period of time. If the questioner can distinguish the answer to be coming from a human being or not, then apparently there's a machine. But if there's no way to distinguish the answer, that means the machine, it probably can be viewed as having the intelligence. The outcome is actually, yeah, there's some super clever programmers have done something clever enough to confuse the questioners. Of course, it's case by case, and there are also cheating, whatever. But that's not the key. The key is it stirs interest to question intelligence. And that's the first wave of intelligence in 1950s. John McCarthy, actually the person who coined the term artificial intelligence. And based on his vision, the intelligence should have several features. That includes perception. That means it can have a sense about itself and our surroundings. It also can learn from experience. Actually, that's when machine learning was kind of came into the stage. People start talking about it's basically learning from experience. In addition to that, intelligence also have some problem-solving ability. They can reason. They also have language, and the list goes on. So this is going to be a very nice time. People start thinking about intelligence. There's a financial support. There's a great scientific interest. The first attempt to solve this problem is basically actually quite simple. People think the bottom line of intelligence comes down to searching. So let's just begin with a simple example. This is a Hanoi tower. I think many of you probably have played it before when you were children or you have done some computer programming exercises in school. So just for those who are not immediately familiar with the setup, I'll just iterate briefly. So you have a pile of donuts here. They have holes in the center. So the goal is to move the whole set from A to C in the end. The rule is during the whole process, there's not a single moment that's allowed the bigger one, the bigger donut, go above on the smaller donut. So as you see here, there's going to be some kind of moving back and forth to ensure the order is correct, which is the smaller donut is greater than the bigger one. And this problem apparently can be solved by searching. Actually, there's a famous, people probably who do coding already, is the stash algorithm. Do this quite efficiently if the file is not too big with a modern computer. Of course, among all the searching solutions, there will be one optimal. So there's a particular optimal solution illustrated in this picture here. Then basically the intelligence or the beginning step for intelligence goes down to the question for searching. It was kind of exciting for a period. Then the problem came. Sooner or later, people realized some problems is not easy to search. For example, this one is a golf game. Based on statistics, there's about 200 moves if people anticipate every 4 moves on average. And if you do the whole thing together, the total numbers goes to just astronomically, very rapidly. With the old days computer power with today's computer power, it's become very challenging. So that's actually really threw a big question about the fundamental validity of intelligence. Even the people start asking whether this hypothesis was even worth pursuing. A lot of people who are very famous in mathematics and statistics actually stood up against the development of the intelligence. And then that came the Ice Age, the fourth Ice Age of intelligence. And then the time came to around 1970s. People realized, since we're talking about intelligence, instead of going about some other algorithms, why don't we just capture human knowledge? What that means, that's basically build a bunch of a logic system so that machine can reason as humans. For example, here, if an animal can fly, can lay eggs, then there's a bird. If a bear can have a black and white color on the surface and eat bamboos, and there's a giant panda, something like that simple. I also can be reason. For example, all humans can use tools. John's a human, then John can use tools. Also, all scientists are smart. Giuseppe is a scientist, and Giuseppe is smart. Of course, you can see clearly, the reason may have flaws. I'm not saying, in particularly this Giuseppe case, I'm trying to say, there's some loss. For example, the purpose of wings to fly. Birds have wings, so birds fly. But there are some birds don't fly. So this kind of situation is getting not difficult for human beings, but very challenging for machines. So also, with the huge amount of human knowledge available out there, it's really hard to actually understand where to start and how to code the system. Surprising enough, there were some initiative to pursue, but there was not really a concrete ending. So that set the intelligence into another small dip in the history. Then came to 1980s. It's pretty much driven by the development of robotics. People view intelligence should be an emergent property. That means there's some kind of consequence through the interaction with the environment. So that's a new age for AI. It's called actually agent-based AI. And of course, as we mentioned already previously, there are some logic nodes and some uncertainty. So there has to be some statistical algorithms allow people to cope with uncertainty. One of them is the Bayesian theorem. I think many of you already familiar with it, but just for those who are not yet, I just throw in one simple example here to illustrate, how this particular algorithm helps us to address the uncertainty issue. So this is a very typical setup for Bayesian theorem. There's 100 people out of 10,000 women for age at a certain age will have routine check for the breast cancer. It's known, every 80 out of 100, which basically 80% of the cancer patient will get a positive outcome from something called a mammogram, which is a medical test. Also, 95 out of 9,900 women without cancer will also got some positive result, which is false positive. That's quite common. There's nothing 100% for sure. Actually, that's about a certainty. So the question is, if there's 10,000 people out there in the group and start routine checking, what fraction of women with a positive outcome will actually have a cancer? Well, this is kind of interesting question. Based on human intuition, if you think 80% people who got cancer got a positive result, you probably just quickly jump into the conclusion that's probably somewhere not far, maybe not exactly 80%, but close enough. Actually, it's a little surprising. If you really set up all the mathematics to calculate the condition, which plus is a condition for people who have a positive outcome, and actually they have cancer, and you basically use the law of total probability, you end up like 48%. It's more or less, I would say, flip a coin. So yeah, apparently that's kind of surprising result. Many medical scientists still kind of being challenged by that. Especially today, when we think about all the tests we are doing now in many contexts. So just something bear in mind, there's an uncertainty out there need to be addressed. Of course, more recently came to the neural network, especially the hardware deep learning has pushed intelligence to another high level. So neural network, it's basically can be illustrated by the graph here, where you have some input signals through some matching, and these signals got set into the middle layer, which is also called the hidden layer. And then again, after some process, it has been output into the output layer, which is the final result. In this process, people has actually developed so-called universal function approximation theorem. That means if you have a single layer in this neural network, it's sufficient enough to approximate with enough precision for any function. So that's pretty much motivate people to continue this kind of research. It's quite exciting. It's quite interesting. And the challenge came that as you want to approximate more and more complex functions, this in the middle layer getting more and more complex, the way to estimate the weights become very challenging. Actually, for some time, it was quite desperate to get this weight precisely and to proceed with the approach. So that's limited the application for this technology for some time until not very recently, but recent enough, and people came up with a backpropagation algorithm. It's pretty much an optimization, allow people to estimate the weight, plus the huge increase of computer power. People can really leverage the neural network, especially deep network, with the complexity to approximate a lot of real-life scenarios that are far beyond many conventional mathematical methods can achieve. So that's basically where we are, and most people talk about intelligence, which is talk about deep learning. And along this process, it's also another way to define machine learning. It's basically to generate output without a recipe. So as you see here, we talk a lot the history. During the course of history, machine learning was mentioned multiple times, more or less in the context of artificial intelligence. The definition was given by many people. Loosely speaking, it's not really clearly defined. So until 1990s, there's a professor from IT re-examined the problem and gave a more computer science rigor definition for machine learning. So, which is pretty much written here, highlighted in blue in the background. So he's saying a computer program is said to be able to learn from experience with respect to some task, and also perform some measure on the task. If its performance on the task based on the measurement of P can be improved with experience, then this program is said to be a learner. For example, a computer program can learn playing a Go game. It can improve. It's probably going to improve its performance measured by the chance to win through experience of playing against itself. So this is one typical example for so-called reinforcement learning. So this is now, by this point, we got a clear definition of learning. With that, I'm going to move on to a little more details about learning algorithms, which is all of your interest here. So machine learning, if you look at it categorically, there are pretty much two types of learning. One is so-called supervised, the other one is called unsupervised. Supervised learning can be, use an analogy to be viewed as learning with a teacher. So there's a teacher can provide the questions, know the answers, and the students learn through some access with teacher. Then in the end, the teacher will offer the authentic outcome, compare students' performance, and give a evaluation. So that's more or less the setup for machine learning. Put it in mathematically, it's very much like this. Given a random pair, which is x and y, x is a matrix, is a design matrix for your system where you have a lot of features to describe a particular outcome. Y, it typically called a response. It's normally a vector. It could be the global temperature, can be the fish distribution, can be rain precipitation, or whatever you have interest. Normally it comes out a vector. The task is only seeking a particular function for the aim that to optimize this loss function between your original response variable and the estimated function, which is came out from your approximation. By minimizing this one, you achieve optimality. So that's pretty much the setup for the supervised learning. And GCP will talk a lot about on this subject in the geo applications. So I decided to go into a few more interesting discussions around this aspect. So if you talk about machine learning in the supervised context, one of the interesting things you want to ask is about the error, how good your prediction is, in other words. Well, commonly people will break down the errors of machine learning into several groups. So this is the function, as we showed before. G is the learner you have come up with and has been trained on a particular site for the tau among the rich class of all the functions available, big G. So you want to estimate the risk of this particular function through your training. You basically can break down this formula into several components. One is the optimality, to optimize the function itself. It's also called irreproducible error. And that's something you have to live with. There's nothing you can do by improving the algorithm or collecting more data to improve. So we just leave it. And more interesting part becomes these two terms. One is actually describing the difference between this particular optimal point and the last functions available in this in the entire data set. So this is error also called the approximation function. Approximation error is basically describing in all the functional space what's the availability that you can identify a particular one that you get this loss and you can achieve this minimum. So that's talking about the functional part. The second one is called estimation error. That has to do with training, because among all the function site, which is indicated by the big G here, there are so many options. What you have is you only use the training set to train a limited available data and in a limited small subset of the entire database. So that also have also induced some error. It's called estimation error. That's normally people have a lot of interest about. So put into another more applicable context, which many people use, which is the L2 norm or square loss. So square loss is basically, you actually estimate the expectation loss of this particular function and your optimality, right? This is your true function that you aim to gain. And you have a full set of the data, which is complete set of data available and a complete set of function available. You want to estimate the loss here. And this can be break down into basically two terms. I didn't want to go into the details because there's a little bit duration to go, but from the moment, just take the face value here. What it's saying here is this particular term, which actually really concerns the performance of your model, can be broken down into two contributing terms. One is the estimation of the function itself minus the true optimal. That's also called bias. And this is the square bias the other term going to be this function, the variance of this function. So what is simple formula is trying to telling you is there's a tug of war between these two terms when you're trying to build an estimation function. So what variance tends to do is, you want to enrich the model complexity so that you can reduce the bias. So the more complex model you have, the higher chance you can reduce the bias. But on the other hand, when you have more complex model, you increase variance. So you see here this kind of balance point you're trying to toggle so that you can find an optimal. This is showing here. So probably people are more familiar with terms of overfitting and underfitting. That's basically talking about this is a mathematical representation here. If your model goes too much complication that has fitted data to its absolute accuracy, and you totally ignore the noise and you have other impact, you probably end up with overfitting scenario. Or if your model was so simple that doesn't have enough capacity to capture data complexity, then you end up on the other side of the equation. The goal is trying to identify this optimal point in terms of model complexity and the predicted error. Normally, it's somewhere in between. Giuseppe will talk more about this in his presentation. Now, we finished the supervised learning. Now we move to another topic, which is unsupervised. My personal feeling that it's going to be more interesting. So previously we said, the supervised learning is going to be an estimation of the expected loss, where you have an optimum y value here. The response variable here. But now, because we don't have a particular teacher, we don't have a reference. So we have a broad landscape to explore without knowing the correct answer or not. It's all you define. So the optimization function goes back to the form like this, which is the loss becomes the loss of the original feature function and your approximated feature function. Let's just throw in a few more examples regarding to unsupervised learning. I think some of mapping, probably some of you have heard about it. It's basically a dimension reduction technique. Let's say, suppose you have original data present in day in the data set of a vector, and that's dimension for this data set is in D space. Now we are seeking a new set of representation for this set so that the output dimension will be reduced. In other words, we want to compress data into such a way that we can capture a feature better, but also we want to preserve the distance in the original structure. In other words, just do a miniature of a bigger subject. For example, you have an airport, airplane, but you can build a smaller one as a toy, but also has a full functionality of the original big plane. Mathematically, it's written as such. You have an original distance and reduced distance. You estimate the performance by basically the mathematical expectation, and you evaluate in each step in the iterative function until you reach confidence. So apparently this is going to be, you can see it's optimization process, and it used a stochastic designed algorithm to achieve the final optimal point. So another one probably even more familiar to you is a principal component analysis. It's also a technique to many of you use for clustering or dimension reduction. In this situation, what we have is a little different setup, but with similar goal compared to standard mapping. So in particular, where we have data in the D dimension, we seek a particular set of orthogonal basis to re-represent the original data, under the condition that these bases are normalized to 1. To put into a more mathematically explicit context, it's pretty much trying to maximize the variance, which is shown here. It's basically expected square, as shown before, and this constraint here. The technique we use is just using one way to do it. It's using the Lagrange multiplier. I'm just using the first component to demonstrate how this thing is done. As you see here, this is another example where optimization has a big play in pursuing the machine learning solutions. One more example, maybe this one has not been obvious or so popular to many people. It's called a self-organized map. The idea here is basically trying to use the analogy of human brain and how our brain functions in the recognition process, and transfer that into the pattern recognition and the feature extraction. So in our process, human process, when we recognize an image, when we hear about a talk, we normally will pass the input signal elevating our brain and send the signal to a particular domain. It's like here, demonstrating there's a language center, vision center, coordination center, or many other domains. And to use a mathematical representation for this particular phenomenon, we use so-called competitive neural network, where you have input signals through some weights, you arrive at the complete layer, and in the end, you have a one particular neuron, which is called using the winner-takes-all situation, where you're going to excite and pass out the signal. Algorithmically, you have three processes: computation, cooperation, adaptation, and that's how you combine a signal, excite the neurons, and transfer signal in the end. I'm not going to go into great details in here. I'm just trying to finish this one with the last one. Many of you probably already familiar with. It's called Deterministic clustering. In this scenario, we want to classify the data in the original space into a cluster space. In this particular situation, we give a preset number of clusters we have in mind. We evaluate the L2 norm between the original data and the center of the points, which is estimated here. That's where the k-mean come from. And again, you see this is the evaluation of loss function. It's going to be optimization process. So far, the drawing point I'm trying to get to you is pretty much here. During the unsupervised learning process, optimization plays a great role. So if you think machine learning is a very interesting subject, then study optimization will be very helpful for you to have a deeper understanding about this particular subject. So how I'm doing with time? Shaba, how much time we have? I didn't check when I started. Do I have another 5 minutes or 10?
I think you have like 40 minutes already. Like I don't know whether you want to spend how long you want to spend.
Okay, I was thinking we have 2 hours right now. I realize I'm already kind of hitting the 2 hour point. 1 hour point, sorry.
But since we start later, do you? I mean, if you are free later, I mean after 2 hours, like we can continue till like 10:30 maybe. Like
okay.
No other obligations.
That gave me a little more flexibility. Yeah. So I think my talk is intended to be about 40 minutes. Then have some question and answer sections. So now I think it's about the right time. Okay, perfect. Thank you so much. All right. Yeah. So far we have been through all the intense, rigorous part, and I won't tell you more interesting, which is that's not enough. So everything we have discussed so far is based on the assumption that we understand the error, and error comes from either the function part or the incomplete representation with your data. But we don't know many other factors has been in play here. I will throw in several high-level philosophical conversation here to entertain you, and also I think they're quite important. The first one is about the data itself, the presentation of the data here. So I'm showing a figure in front of you. I think many of you will see this figure as a sparrow. It's kind of going down inside and kind of convert in center. But actually, the fact is, if you really trace down a particular circle, like I'm doing here with my cursor, it's going back to origin. So it's a closed circle. So the setup is all these circles are concentric circles. It's just the all these stripes and with the decorations kind of cheated your vision system to think this is special here. Another example, which is a very interesting triangle, which doesn't exist in the Euclidean space. What's showing here is you can really follow the trace of the space and continues with no ending. And this particular space figure can be represented in a kind of a projected fashion as I'm doing right now. But in our real world, it doesn't really actually exist. And this one is probably more interesting. I'll just pause for a second, and I hope the audience can just staring at this figure. It doesn't long, maybe take 5 seconds. So I don't know what everyone is seeing. I can tell you what's in my vision, right? So you first see a couple flowers, a bunch of flowers, then you also see a vase. But as your vision has been focused on this graph, and with time, you see it's kind of a quick movie, the flowers are put in the vase. So this is kind of another famous example to show how our vision is actually where they configure something of the original data before they send to our brain. So that's the right question, whether seeing is believing. Or in other words, whether the observation itself can be trusted as they are. Well, actually, that's not the end of story. It's not only the observation, there's also measurement. This is example very famous in quantum mechanics. We call it Schrödinger's cat. What happens here is there's a radiator showing like this symbol. At random, I'll send out particular alpha particle. If this alpha particle being sent will trigger some device to hit a particular flask, and this flask has some poisonous gas. If the signal being passed here, the lever will act, use a hammer to hit the flask, and the gas will come out, the cat will die. If the particle was not released, of course, the cat will be happily leave in the condition. And this is set up in a particular box. And then this dilemma comes, before you open the box, you actually don't know what kind of life status of this cat. Based on the quantum mechanics setup, it's going to be a superposition of both life and death, which is pretty much incomprehensible. Well, I mean, if you really think about quantum mechanics as one of the pillar knowledge human beings so far have achieved, we can check out this one. So this one is a time-dependent Schrödinger equation. It's pretty much like equivalent of dynamic Newtonic dynamic in the microscopic world. The only thing I want to show here is basically the explicit representation of dynamic system is totally deterministic. However, if you look at a solution of this system, you see this wave, these moving blue and red waves are actually the solutions of Schrödinger equation to represent the real and the imaginary part. You see it's actually dynamic moving, and the result is not a particular point value. It's actually a wave. The statics of the quantum interpretation is going to be a likelihood, which by this square mode here, that's in other words means you started with a deterministic system, the solution become probabilistic. So what's that supposed to mean? We started with a deterministic root, then we arrive at a probabilistic fruit. Well, I think nobody understands. Even the famous people in the field for many years, nobody can understand. But regardless we understand or not, it's something real. We should not ignore. Well, if you think the quantum world is a little far away from us, we still have another aspect to cover, which is more close to us, is the deterministic world. Everything we think, from Newtonian mechanics, we think as we have been given the momentum and position of a particular object, and we can make prediction of everything by itself as long as the starting point was already known. That's actually claimed by the Laplace demon. We, by default, also accept it, but should we? This is a simple example coming from the deterministic world. It's a logistic mapping. It's coming from logistic equations. People use quite a lot in biology, chemistry, many other fields. It's basically described, can be used to describe population dynamics, change of many dynamic systems. The point is, this system is totally deterministic. But I see in this particular equation, there's a parameter r. As you configure r along the real axis, you notice in the beginning, it's kind of all, following the deterministic trajectory. But as it starts reaching particular points, the system starts oscillate or bifurcate. And the bifurcation has certain features. As you more force down the axis, the segment or distance between the points to start bifurcate becomes shortened. It follows a Feigenbaum ratio constant. Nobody have now yet claimed to fully understand it. They appreciate it. But this is another case of deterministic example where we start from something absolutely known until something we're not certain. So with all being said, what I'm trying to show or discuss with you is basically whether we have to relook at the problem of the modeling and prediction from a high level, whether we have captured all the necessary assumptions and groundings before we even begin to start about the modeling errors. With the three examples about the inaccuracy in observation, the measurement, the quantum mechanics setup, and the uncertainty arising from the deterministic world, should we reconsider what uncertainty means in our study, especially in the context of geomodeling? Geomodeling is very special in the whole modeling world because it cares about, in many ways, the variations in time and space. And so far as we know, time and space are both important parameters in our knowledge to understand the world. So it's highly relevant, it's super interesting, and it's full of opportunities. So I just posing here for everyone to think about where we can go and how about opportunities we may have to tackle the learning and intelligence problem through this particular interesting angle where people may not have thought too much in the conventional approach. So my take on this has to do with the consciousness. What is consciousness? Well, it's an interesting subject. It's pretty much like time. We use time all the time, but nobody understands what time is. And so does its consciousness. It's a concept in psychology, but it also ties closely to the physicist. In quantum mechanics, people use a lot of consciousness, need a lot of assumptions. Even in mathematical world, this is a famous mathematician. He also has his own concept about consciousness. And people can, the audience can read more from these lines and interpret its meaning. Also, Einstein mentioned that the problem cannot be solved at the same level of consciousness that's created. So I think people are very clear. I hope I have made myself clear where the direction I'm trying to point towards. Just think creatively about modeling, about machine learning. Consciousness is a very important factor in play here. And that's pretty much the end of my talk. I think I'm doing all right, exactly 40 minutes on time. Thanks for your attention. If you may have some questions, I'll be happy to entertain with some answers. And the next one will be coming on the stage. It'll be Giuseppe. So I will just pause here, stop sharing. Should we open the floor for question now, or let Giuseppe continue?
Longzhu, it depends on you. Whether you want to take question now or after Giuseppe.
Well, I mean, since I've talked quite long, maybe people have questions. Let's see if people have questions. Then I can handle right now.
Yeah, we can.
If not,
like,
I'll just
have like several minutes, like 10 minutes for you to have question and answer session.
Okay, sure, I can do that.
Yeah.
So yeah, I rambled on a lot. Quite interesting, hopefully, materials.
Yeah.
Anybody may have comments or questions, even discussions. I'm happy to talk with you. So, do they just post in the chat box, or they can also speak up from their speaker?
Yeah, you can just direct your questions to Longzhu directly, or write down your answer in the comment box. Longzhu, maybe I can ask a question to you.
Sure.
Like in machine learning, there's always the problem of like overfitting. I actually don't quite understand what is the problem of overfitting, and what's that problem and how can we solve it?
Yeah, great question. Thanks so much. Overfitting. So okay, optimally when you do the supervised learning, right? You build a model. The ultimate goal is trying to make predictions on the future or on a particular site that has not been seen by the data. And overfitting basically means your model has a very good performance or super good performance that in the training data set. But once you take out the model, start making predictions on the unseen data, your performance degrades. The reason for that is basically due to the fact that the capacity of your model you use have been so high that it can fit a lot of details, unnecessary details in your training data, and that causes the embedding of noise in the model. Of course, when you lift the model up and apply to some unseen data, those particular noise may be different, the features may not be true, so your model bury a lot of great detailed features about noise, which is not applicable into the unseen data. So that's normally people call overfitting. Yeah. So the way people to handle it is kind of a technique. It's also quite challenging. I don't think there's a definite answer over there. As I mentioned in my talk, it's going to be a balance between the bias and the variance. So the bias is trying to minimize the difference between your training model, the training function versus the retraining data, and the variance is pretty much the complexity of your model. So the more complex your model is, the better chance for you to fit details. But at the same time, when you increase complexity, you also increase the variance, which is not good for you. So your task is going to be find an optimal point between the bias and variance, so that you can see the model is properly fit to get the main features of your training set. And also at the same time, don't sacrifice when you start making predictions outside the unseen data. So that's why you have to do the training and testing, all these techniques you normally do as a modeler.
Mm-hmm.
I hope that more or less answers a little bit.
Yeah.
Yeah, I think it's pretty good. And my talk normally, get a very good message across the board. If there's no more questions, I think we can move on to yield the floor to Giuseppe.
Yeah.
Yeah.
I have a question.
Okay,
sorry to interrupt you. And
no problem.
My question is still similar to the previous question, like the trade-off between bias and variance. I'm just confused. Like, is the trade-off between these two applicable to like every machine learning models? I know, like in the linear regression, we do that. We do some trade-off. Like we use some functions like LASSO, LASSO to tune the best lambda in that trade-off. So, for example, like for a random forest, do we have to do that?
Okay, thanks so much for the great question. Yes. Yeah, actually, when I did my talk, I kind of intentionally avoid a little hot topic over there, because if you look at my initial setup, the error estimation, I have a approximation error and estimation error. The estimation error, which is kind of our interest, is not well defined unless you specify the loss function. And the loss function we normally use is basically square loss. As you mentioned, that in the linear system, you use log. And in linear system, the square loss has been well characterized, and you know all this already. But if you bring up this one to a different system, a nonlinear system, for example, random forest or other techniques, doesn't matter what it is, they have this kind of a tug of war between the approximation and estimation. Approximately can be viewed as the bias of virus in a similar scenario. The one you talk about, lasso, is one technique people have used in the linear system to reduce the complexity of the model. But similarly, in random forest, you also can control the growth of forest or trees, so that you have some impurity parameters or some other controls to control the entropy of the system. Actually, random forest internally, they use entropy terms to estimate the model accuracy and the purity of the forest. So in short words, there's a quite analogous approach in quite a general. In the technical details, they vary a little bit, but the overall direction is the same. I hope that's not more confusing.
Yeah, thank you. That makes sense. Thank you.
All right. I think I don't see more questions. I will just pass on to Giuseppe. Giuseppe, you're on.
Yeah, thanks, Lunzu. 1 second. Okay, can you see the slide? I think so, yeah.
Yes.
Yeah, can you hear?
Yes.
Yeah, perfect, thank you.
Yeah.
So thanks, Lunzu, for this introduction in the fundamental of machine learning and artificial intelligence. And now we move on how to implement this fundamental in environmental application by combining GeoComputation and machine learning. I've been training as a forest scientist, but later on in my PhD, I was starting to developing everything under Linux environment. And now I can talk with the computer scientist and also with the statistician to apply the different technique in the geo-application. And now we will carry over a bunch of examples that we carry out through the years, where I emphasize the combination of GeoComputation and machine learning together. So nowadays, we really are in the world of data. Data that are coming from different sources to really scanning the entire surface of the Earth, going from the ocean to the land to the mountain, calculating the amount of precipitation, kind of aerosol, atmosphere content, and these are really really big amount of data that quite often are even carried on by animals to the so-called the biologging revolution, that are really the transport, the checker sensors that are really able to scan in the entire ocean, even bird transporting the sensor for the temperature variation in the atmosphere, and so on. So all this kind of data, they bring us really a lot of information. We need to have mainly two fundamental skills to dealing with this data. In particular, one is the geocomputation, and the other one is the machine learning. These two parts, they are really, the geocomputation usually come first in the data preparation that correspond in the downloading, reprojection, pixel extent, alignment, that this is really important, mosaic, non-raster and satellite image, tiling, gap filling to avoid, to refill the gap through the satellite image, and different kinds of temporal spatial aggregation. These usually are really extremely time consuming because you need really to mastering very well all the different software that are dealing with the geocomputation. And you need to really really picky, let's say, especially in the pixel and extent alienation, in order to not having issues later on and in the data, in the final data population. So over here, you really go in the so-called data standardization, data squeezing and summarizing and everything. So your data from very big, they can become less big, smaller, a bit smaller, in order to be able later on to ingest inside to the machine learning algorithm. For the machine learning algorithm, you need something extremely important in terms of selection and constraint. So understanding really the fundamental of the machine learning algorithm as Lonzu was driven. You have to really be clever in that understanding how to do the sampling distribution and the splitting procedure in your observation data to avoiding and to study potential overfitting and final errors. You need to also learning the algorithm in terms of how you can tuning, okay? How you can tuning random forest and how you can tuning neural network. And actually the tuning of neural network, we saw this lecture that we are running, are really important to achieve a good result. And finally come up with a validation procedure and the accuracy assessment. And finally, you can driven some final conclusion with the variable importance, understanding where you have root mean square error residuals in your map and so on. So all these two techniques, they quite often come first the geocomputation and later on the machine learning, but they are really interesting. Sometimes you can have a very big job, let's say in very important big job in the geocomputation part, and some other are more prone to the machine learning. But all of them, they come together in the real world application. So in this context, we will see different topics that have been evolving through the years, that have been studied and coding in this context. So some are more geocomputation and some other are more machine learning. So we'll talk see the application in geoengineering for geocomputation, in geomorphology, and in global hydrology, hydrography. And then we will move to machine learning application in different parts like landscape genetics, nitrogen and phosphorus concentration, nitrogen emission, and freshwater discharge. Okay, so let's start with geoengineering and let's see in brief what it is. So geoengineering, I don't know if you heard these terms, but is the modification by humans of the atmosphere or also other part of the earth to, let's say, to alleviate or reduce the effect of climate change. Okay, so there are several techniques for, like, for example, inserting aerosol in the stratosphere to reflect the sun, the radiation of the sun. This will produce like an opposite of green effect that reduce the amount of radiation coming to the earth. In this context, I've been working in 2018 with some clever scientists that we have been developing a method to understanding what was going to happen in case of aerosol injection in the atmosphere, and the so-called implementation and termination of the geoengineering effect. So in practice, it's very simple to spray aerosol inside the atmosphere, and you can do it with the airplane in very, let's say, not a really expensive way. So you will have, if you see over here, you can see the red line going up in terms of climate change scenarios that is going to happen in 50, 60 years. So what is going to happen now, from now on, let's say. So if you implement the geoengineering effect, you will have a drastic, brutal decrement of temperature, okay, that is quite stable later on with the spray, continuous spray of the aerosol inside to the atmosphere. The temperature will still growing, but what is happening at one point, there is the so-called termination of the effect that can be due to misunderstanding or some war action or some government that don't want to pay anymore the aerosol injection and so on. So we will have a brutal increment of the temperature until arrive where it's supposed to be. Okay, this can happen in the temperature, but is also happening in terms of changing of all the precipitation pattern. So in this context, you can study really the changing and how much fast this change is going to happen with the so-called climate velocity. And the climate velocity is nothing else than the rate of change of the climate versus the through the years versus the space. And in this context, what is going to happen if that the animal or the plant is not able to move so fast to the space to keep it up, to be in the same envelope, the animal will be extinct. So so we map this climate velocity, and as you can see in this slide, you can see that we have this bivariate map that really show you what was happening in terms of termination. So in case of termination, you have a climate velocity that is going to be much faster than the usual climate change. This is coming back also from the previous image that you saw, that the steep of the curve was really really steep in that terms. In this context, you can see that you can finalize that an organism would have to march faster and faster to stay in the same climate envelope, to particular envelope, to avoid the so-called extinction and so on. In this work, I was working with several mainly climate data, using climate data operator CDO, an open source software mainly for net CDF data, and we were combining and crossing over different data sets for climate change scenarios and doing all the representation that you saw so far through scripting procedure. So quite an achieving study that has been published in 2018 in Nature. Later on, I was also working in geomorphology. So a few words about geomorphology. So geomorphology is nothing else than the study of the shape of the Earth in the different context of the relief terrain. As you can see, they can really have different shape and forms, and these shape and forms, they really modeling the microclimate and microclimate ecosystem in the different parts, and you can really summarize the different geomorphology in according to the curvature, in according to the profile and tangential curvature, to the slope of the terrain, the first order derivative as the slope, or in one direction, north to south or east to south. So this tremendous data set that we have been producing in 2018 with a publication of scientific data, so-called Geomorph for 90 meters, is coming directly from the digital elevation model MERIT-DEM, developed by Dai Yamazaki at the 90 meter resolution global level. So with this digital elevation model, I was able to extract different level, different kind of roughness indices and curvature that really characterize all the different different part of the world. And you can see in the following slide that you can have a different kind of roughness, for example, or curvature in terms of profile curvature or tangential curvature. So all these layers, as you can see, that as I mentioned before, that are really important for animal movement, for microclimate condition, micro and microclimate condition, can be later on used as a predictors in machine learning environment, because microclimate, we have temperature, but what is really related to the micro temperature in close to the Earth is really, for example, the position, if it is shape facing to south or to east or west or ovest and so on. So these are really embedding different kind of microclimate, can then later on can be useful for species distribution or for other kind of pattern analysis. In this context also of managing digital elevation model, I was also working in the global hydrography. This is an ongoing project that is carried over from already 2 years. That is, the final aim is to mapping the stream network at 90-meter resolution using the merit data digital elevation model. In this context, we have ancillary data that can be used for understanding the presence of water, and these are the coming from satellite images. So from 2017, PECEL has been released an amazing data set in terms of accuracy of water coming from Landsat data. The satellite image in the stream network can tell the presence of water for river bigger than 30 meters. But quite often you cannot see small stream, you cannot see the direction of the water. And sometimes you can have also interruption of the stream network because your pixel become not so much accurate to understand the presence of water and so on. And of course, you cannot calculate hydrological parameters like slope of the stream or some others. So in this context, the digital elevation model can really helping us in understanding the flow direction and calculate the flow accumulation, the amount of water in the upstream scenarios, and different other kind of hydrological parameters like drainage direction, stream order, stream length, water speed, and so on. He cannot helping us in understanding water presence, water occurrence, and even water discharge. But he can, the combination of the two, so in terms of stream network and a satellite presence as a water occurrence, can really helping us in understanding the amount of presence of water in the different domain and in area. So in this context, I was using the Merit Hydro, that is an hydrologically corrected digital elevation model, again released by Dai Yamazaki a few years later, the previous one, and I was extracting all the stream network at global level and 90-meter resolution. So you can see that you can really define the different stream network. For example, over here you can see that the black area is the one that I'm releasing, and that is in perfect overlapping with the NHP Plus, that is the United States stream network delineation. That is much better than the HydroShet that quite often is used in the hydrological application. In this context, this ongoing project has been to be released in September 2021 as a data set and also as a publication. And it's quite complex to achieve from a computational point of view, because the software that we have, in particular I'm using GRASS for this computation, cannot ingest the full matrix of the world in only one shot. So you need to work in different tiles, and in this particular are the red tiles. They need to have all the entire basin within the tiles. So there is a lot of computation in terms of understanding what is the dimension of the tiles, how much the overlapping that has to be computed, the cleaning procedure, and of course all the standardization in terms of extent and pixel resolution need to be really achieved at a really fine resolution in order to have everything in place in an appropriate way. Then there is also the second tiling system, the green one, that again you cannot release it the full data set in only one shot because it will be quite big, so you need to tile it again in the in square, in tiles that are more consistent. So all these procedures is in process, and we are in the process of writing the publication and also validate our final product, and again will be released in 2021. So far, we have been see different kind of application in the geocomputation that rely on really massive data process, especially this last one is quite complex, the achievement that we are accomplished. But let's move in some other example that are more related using machine learning. One of these is really one that came out really a few months ago in landscape genetics. Let's see what is just landscape genetics. Landscape genetics is the scientific discipline that combines population genetics and landscape ecology. So what does it mean? That the different animal in this context, they can have different level of movement in according to the natural barrier that there are in the territory. Okay, so for example, over here you can see that if there is a city, some animal that cannot crossing over, and so on. So this, what does mean this one? That the two population, if there are some barrier, they cannot move, so the two genetic population cannot be crossing over, and so the genetic will be quite different. So in this context, we were studying Aedes aegypti, a little mosquito that has been appeared 100 years ago in the United States, coming from Africa with the boat, with the humans. And we were studying the genetic difference between the different population that we are in the different point. So over here you can see that there is already a clustering among all of them, and you suspect that there are already some barriers that do not allow the movement of the mosquito. So we were using different response variables like land and water, so land cover variables, climate variable, because all the species, animal and plant, are really influenced by, especially by temperature and precipitation. And then we were also using the human infrastructure, because the mosquito can really hitchhiking with the human and also with the transportation. This has been an amazing work where has been combining different level of geocomputation to manipulate all the different variables, and also to create a machine learning model later on in the with an iterative process. So in this context, we were calculating the potential movement of mosquito through a cost path analysis, and the cost path analysis has been done previously in R. Then for computational reasons that we cannot running so many iterations, so I was translating everything again in GRASS, and we could achieve really high level of computation because we were able to use a software that is much prone for this kind of geocomputation analysis. And over here you can see the final map of genetic connectivity, where you can see that the animal, the mosquito that have really high level of connectivity, so they are genetically more close, and the so-called surface friction of the landscape. This one was accomplished in more or less 3 years of work with the PhD student that I was supervising. In terms of nitrogen and phosphorus concentration, over here, yes. So over here, nitrogen concentration are really responsible for eutrophication of the water. Eutrophication of the water is the concept of big amount of nitrogen phosphate in the water that produce algae blooming that not only block the sun radiation, but also when they die later on they start fermenting and also consume all the oxygen inside to the water. In this context, with Lunzu, we really building up a machine learning model to use the different water quality sample in the United States that are changing according to the location in terms of presence. And we mapping with the different environmental predictors that are listed over here, among them all the different land cover, land use, temperature, and precipitation. And in this, we training the random forest model, and we saw that, for example, immediately you can see that all this area in the United States have high level of nitrogen phosphate due to the big amount of agriculture and grazing activity that is in that area. This was really quite complex job to achieve from the data analysis, pre-data analysis point of view, because the data set they were really noisy. So Lunzu was really working on the data cleaning and preparation, and in final machine learning model was coming out later on in this context. So this one was also used mainly R for the machine learning part and GRASS for the different geocomputation analysis. Another work that we have been also working in the last 2-3 years is with nitrogen emission. This has been achieved with the publication in 2021 from Mazzadri, myself, and also Lunzu, where we were studying the emission of nitrogen in the different stream in the global or semi-global level. As you can see, is missing the northern part. So we were understanding that the small stream have really strong impact in the emission of nitrogen emission. In this context, we were using the previous technique of calculation nitrogen phosphate concentration, and then use the output of nitrogen concentration in a physical model to achieve the total emission. So over here, we were combining machine learning and physical process model to achieve a best result in the modeling phase. So we move on in the last job, and also the big one that is strongly related with the calculation of the global hydrography. So the freshwater discharge. So with the first work, we were really understanding with the global hydrography, we were really understanding where are the streams, and with the second one, we try to estimate the amount of water in a particular location in terms of a 90-meter resolution. So what we want to achieve is really to quantify the metric cubic per second, so the discharge at 90-meter resolution at global level, firstly at monthly level, and then we will move into the daily application. Also, this one is quite complex as a work from the geocomputation part and also from the machine learning part, for a simple reason, because whatever is happening in one particular location over here, where you have your gauging station, for example, over here in the basin, over here you can have a gauging station, is influenced what is happening over here in the upstream. So in this context, you really need to calculate whatever is happening over here in terms of surface area, in terms of precipitation, and then transfer it downstream, and not only downstream, but in every kind of in every cell of the stream network. And you can do perfect the same, calculate the amount of forest and the amount of agriculture that are contributing to the water quality and also water quantity in each single pixel. At that point that you have all the predictor, you can build up your table. This computation has been done mainly in GRASS, and you can building up your table where you have your gauging station with all the different predictors that are coming from the upstream condition up here. And over here, you can build up your machine learning model where you have not only one simple formula, but quite complex, where the different weights are influenced by the different weight, are influenced by the different condition. So we are now building up all the variables that are contributing to the upstream, to understanding and building up the table, and later on we will insert in different machine learning technique to really try to extrapolate the flow in the temporal domain, in the monthly level, yearly level first, and then monthly level, and then daily level. So all this kind of work, they really have something in common between them in order to master this GeoComputation machine learning. You need good knowledge, or extremely good knowledge, of Linux operating system for massive data process, including in the HPC. Both of us, Lonzu and I, and all my collaborators are working, for example, in the Yale supercomputer, and they really need to master very well the supercomputer in order to achieve high computational work in terms of both GeoComputation and machine learning. So these are the two other points that you really need to understand very well: the algorithm, the software, and the code of the software that you're using in order to understanding what to do and how to implement it. And the same for the machine learning software. And also, when you squeeze in so much software in terms of massive data process, over there you reaching some memory issues that you have to be able to debugging and understanding what to do to avoid this kind of RAM limitation and problems. So this kind of job and scripting procedure, unfortunately, you cannot do it in only one language. You have to have mastering really different kind of language, and we, Lonzu and I, are really Bash oriented as a gluing language for the different language that we are using around Bash to really getting the maximum that we can do it with the different software, and to get the best that is over there in the market. And we go through, for example, very old language, Oak, for text manipulation, that is still one of the fastest, even better than Python, but are still really super powerful for text manipulation. Then we move, for example, all the hydrological computation has been done in GRASS with some pre-processing like pixel alignment and cropping procedure and tiling system done with GDAL. And in case we need also some satellite mosaicing and segmentation, we also use Orfeo Toolbox for this kind of application. And in the moment that all the GeoComputation has been done and has been achieved, so all the data are ready to be imported inside Python or inside R for the machine learning and for the graphical visualization, we use scripting procedure to building up the table in order to enter inside Python with only the table that is useful for the machine learning techniques. So we really strengthen this language interaction, because the different language, they need to talk to each other. They are not independent scripts that you can run one by one, let's say, but they are really connected in a really workflow in order to achieve computation that can be run and repeated several times, because you need a lot of time and a lot of iteration for the debugging, and also for the machine learning operation for achieving best root mean square error, avoid overfitting, and so on. All these different technique has been teaching from already 15 years in summer school and long-term courses also that has been done previous pandemic in presence, but now we also building up a new web page. In particular, this is the new web page that you can follow directly in spatialecology.net. docs build, HTML, and Docker index. Over here, you can see all the different material that we have been using for this kind of application, and we have different language and software teaching procedure, including inclusive study case, where they can go in the monitoring from species distribution, temporal interpolation of Landsat image for gap filling, dynamic time warping, estimation of nitrogen concentration. This one is the one that I talked about. So, and now we're still developing to the teaching activity that we've been running. So, for example, now we are in the last phase of running full semester course for Stockholm University that you can follow and see the different subjects that we have been using. So in this context, it's really important to understanding and see the importance of mastering different language to really achieve all the different projects that we have done. Of course, then you have to not only achieving the science, but also the knowledge of that particular subject. And this is also good, is also achieved by strong cooperation with other scientists that are expert in that subject. But having in your hands the ability to really mastering and combining all the different language to achieve all the fundamentals that Lonzu was talking about is really a key point to overpassing all the limitation that other scientists are really facing in this context of combining geocomputation and machine learning together. So with this final point, I really want to thank Shadao for this opportunity, also to show you guys what we can achieve with this, with science in mind. And we open the floor to discussion. And please feel free to jump in and question for the different parts that we have been covered, not only me, but also Lonzu in the previous talk. Thank you very much.
Thank you, Giuseppe. Do we from the audience, do we have any questions?
Can I ask a question for Giuseppe?
Yeah.
Yeah. So, yeah, interesting talk. Can you guys hear me? You can hear me. So, for the geoengineering part, it's quite interesting. I noticed at certain point there's going to be a change. You know, you said in the beginning there's going to be by injecting those materials in the atmosphere, the temperature ramping won't be as fast as expected. And then around 50 years, there's going to be another thing happen. Then the blue curve catch up the red curve. And you said that's due to a war or conflict or government not paying. So is that saying because there's a discontinuity in injecting material in the atmosphere that caused that? That's my first question. The second question, second one will be, you mentioned the climate velocity, right? I understand that's quite important, also the animal following the velocity. But how this engineering will impact the climate velocity also? Thank you.
Yeah, good point, both of them. The aerosol condition, the injection of aerosol has to be continuously done to the time, because it's not something that can remain in the atmosphere when you inject only once. Then through the time is going to fluctuate and arrive to the, in particular they think to that inject SO2 that can arrive and then precipitate and arrive to the soil. So this injection has to continue every year through the time to keep it the temperature raising up, but in that context. So who is going to pay this? Okay, let's suppose that rich country they can pay and they can start to do it, but then there can be some disagreement who is going to maintain this system, and can happen that a war can making the agreement break it, and then everybody stop to inject it, and then of course everything has to come up where it's supposed to be. So over here, and then over here is the high speed of temperature that will influence high speed of climate velocity and change it through the space. So the animal, they need to move even faster than the usual climate change. So it's not really the consequences, the near-term consequence of a climate geoengineering can be good, but cannot persist in the long term. Because if something happened, then you have a tremendous jump to the previous situation. And of course, the speed of climate change velocity has to be very high, because you have a slope very high to reach that level over here. And the animal, they will not pick it up in that terms to arrive in that context.
Yeah, thanks, Giuseppe. It's much clearer. I was kind of surprising because as you see here at the 50 years point, if you stop injecting the aerosol in the atmosphere, the ramping up is really quickly. That's really fast. I thought it's going to be gradually dissipate the impact, but actually it's a kind of a phase transition, almost a phase transition.
Yeah, they expected that in 4 or 5 years, all the aerosols that have been spread, they are just going down, and this has been simulated and tested a lot with volcanic eruption that has been happening through the course of the last century mainly, that they see that after 2-3 years the effect in the atmosphere is not anymore there, because everything has been sitting down to the earth and to the ocean. So they can have really strong consequences later on with these kind of geoengineering scenarios. Yeah.
I think you should send the paper to Bill Gates. He should know about this.
I will. Any other question in this contest? Or I have a question for you, for the audience. Who has been using these tools, and who has been knowing these tools of, in particular, this last one that I was mentioned, GRASS, PK tools, GDAL, in the context of geocomputation, and then matching with the Python for the machine learning, or even with R for the machine learning? We need to. I know that my student Zipeng Tang is dealing now with a lot of GDAL, GDAL and Bash.
Yeah,
And now he's just starting also the use of GRASS. And we will later transition into the machine learning in Python. So who else is going in this direction? And if not, which kind of software and language and algorithm are you using? Zipeng, you can say to your colleague which kind, if you have question, and which are your experience with as a newcomer with this software, and how you were learning, and which one was the process of learning?
Oh, you mean all of these tools? And for like my programming experience is basically based on R and Python. And before I came to your lab, and since we are doing the global tree height modeling work, so I have to use some more powerful tools like GDAL and PK tools. So the interesting thing is we use this GDAL, and we can combine them with R or Python so that we can do more powerful work, to run a script for a global area, maybe just for a couple hours. But if we haven't learned these skills, and we have to do that for maybe weeks, or some of people spend longer time to produce a massive data. So, yeah. Oh, I have a general question about the massive, machine learning based on the massive and multiple source data, like you talked. So my question is like, yeah, how can we select the optimal training and test data if we have like massive, data sets? And the second question is, yeah, this one first.
Okay, so in this context, I think also Lonzu can jump on it. When you have the training and testing data set, you have the full pool of data, and the machine learning and even other kind of techniques, they really work well when your testing and training data are really covering the full data distribution of your observation variables. So if you have only training data set coming from high extreme value and nothing from the low value, let's say, the machine learning is going to fail in predicting the low value. So the data set, the training and testing, they really need to cover the full range of of data distribution from the minimum to the maximum, and also they need to have the same kind of spatial and temporal distribution through the time. This is something that Lonzu can jump on it in how we are going to achieve, and for example, how we achieve this in our paper in the nitrogen and phosphorus cases. Lonzu, you want to cover this part?
Yeah, I can just comment a little bit. I mean, I think it's a great question. First of all, I would say there's no, in machine learning world, there's nothing, there's no winner takes all scenario. It's all case by case study. So it's really your data that can dictate the strategy you implement in the modern process. So in our case, when we deal with the NP, we were facing a lot of challenges, especially with the data distribution, the heterogeneity through time. So we did some mathematical transformation to bring the data more normal-like distributed. We also investigate the continuity over time of those stations. So you can follow our paper. There's a lot of details in there, and you are welcome also speak with us. It's kind of a little bigger than what we can talk just in a 5 minutes scenario. It's really case by case study. But overall, I think what Giuseppe already covered, the main idea is trying to achieve identical distribution of the training and testing, which is not easy to large explorations. Yeah, that's what I'm saying. I see that there's a question in the chat box.
Yeah. Like, I can read the question to you. Maybe. So it's from Joaquin. Hi, thanks for the talk. I would like to ask two questions. What do you think about INLA or template model builder to incorporate spatial temporal dependencies? They are very fast softwares to face high-dimensional models. And what are good metrics to measure the overfitting in machine learning models? For example, random first or XGBoost. So these are two questions here.
Okay, Joaquin. Yeah, thanks for your question. So in particular, INLA, I think is a Bayesian approach. I didn't use so much. I have to say that maybe Lonzu can jump into it. And for some internal testing, we are testing XJ boosting together with random forest in particular in the context of hydrological modeling. And XJ boosting has been really in the last 3-4 years has been really achieving and a lot of attention in the algorithm development and use it of so far we didn't publish anything yet, so we don't have a final result, but we are still working in the use of XJ boosting. And for the template model builder, frankly speaking, I don't know what it is. And maybe if Lonzu heard something about this, and also if you can say something about INLA.
Yeah, I know about the INLA, which is as you mentioned, is Bayesian approach based on Laplacian approximation. So it's a good strategy. You know, we have this painful MCMC procedure in Bayesian approach. This definitely will improve the speed. But you know, fast or small is kind of a relative term. It's really depend on the scale of the data and also your basic modeling philosophy. So from your question, it looks like you are in the school for Bayesian. I think that's probably a good approach you want to take on. But there are also other, you know, scenarios. It really depends on what can be used best. Bayesian is good for certain situations, but it's not. It's an inductive approach. It's very sensitive to certain model, for certain data noise, and yeah, it has a lot of limitations in terms of the performance and philosophy. But many people like it, and it works for some cases, and maybe better for some other scenarios. So I wouldn't think I will hold on for a particular model. It's all up to you to investigate and explore. I haven't done anything with a template model builder yet.
And just to adding up to a more detail in terms of the overfitting in random forest and XG boosting, I mean, it's always the usual situation. You pick up, now in few words, you pick up an error estimator, root mean square error, and if in your training and testing you achieve the same result or very close, then you are not in overestimation. Okay, if your testing is, if your training is very high, 90%, and your testing is very bad, 60%, so then you are in overfitting. Okay, so this is valid, is a rule of thumbs. 2-3%, I would say that you are not in overfitting with difference. Okay, so then of course you can building up different crossing validation procedure to understanding if there is some particular splitting procedure that can highlight potential overfitting, or different kind of errors that you can use it if your error are distributed, is Gaussian distributed or not Gaussian distributed. Some error are better than other, and so on. So Lonzu, you want to cover it up more in this part?
Question is about overfitting. What good metrics for overfitting? Yeah, I think it depends on if you the broader two categories. If you do classification or regression. So if you use regression, I think just as we mentioned that L2 norm and root mean square error is kind of a common approach. But there are also, if you go into the deep learning, there are also other metrics you can use. For example, the cross entropy, also some other particular terms. But overall fitting, I think, and Giuseppe mentioned, you want to assess the relative balance between the performance of your training data set and the testing data set. And there's also cross-validation technologies you can use to assess the internal stability of the model. You can also do some comparisons. But I think overall, the general direction, Giuseppe already kind of covered.
Thanks, Andrew. Is there any other questions from the audience?
Well, if nobody asks questions, I have my last question. It's about the missing data. When we are processing massive data from multiple sources, and we have the data can be at different spatial resolution, and also there are missing data. And how do we processing this missing data? We interpolate them or some other way?
Yes. Okay. You open a very huge topic. It's really depending from the different kind of application. So in the spatial context, we can do spatial interpolation for the missing data, but we can also use temporal interpolation. So the spatial interpolation are always the constraint that the land cover change can influence the spatial interpolation. Okay, and the temporal interpolation, we can have potential issues like presence of cloud or some potential extreme event that can really make it quite complex, the interpolation. So we're dealing with water discharge. In our case, there are plenty of stations in the world, but the continuity of the data, okay, they are not really constant. So sometimes you have 3 months, sometimes you have five years, and so on. So many of the techniques in the temporal gap filling and in the signal process, let's say, cannot really done because you have intermediate situation and intermediate coverage and through the time and through the space that make it really challenging to this kind of gap filling. We are still working in this context, so I cannot really tell you the final answer for this kind of application, but they can really change from the process in the context of where you are working. There are different techniques for downsampling the different spatial resolution. I always suggest not to go, from the really low resolution to high resolution. From half degree to 1 kilometer is a bit useless. I mean, you are not getting so much, but as soon you're getting, from 1 to 5 kilometer, over there you have a bit of techniques. You have several techniques of downsampling that can be useful in this context. And over there you can always, having a good geocomputation capability for harmonizing all your data, and then you use it different technique for the temporal filling. In this particular context, for example, in particular context, if you go back to the web page, you can see over here we have an example of temporal interpolation of Landsat image that we were using as a study case in the analysis, and we were interpolating the gap filling with different technique. In particular, we were using Savinsky-Golay technique and also Stefan and Akima spline, and Lonzu was also covered wavelet transformation for the gap filling. So Lonzu, you want to say a few words about this gap filling and missing data and so on?
Yeah, what I want to say is, when you talk about filling missed data, it's basically you're talking about approximation. It's already building a model. So you cannot fill data without a model backbone. So it really depends on your purpose, right? If you want to fill data, you already implement the data, implement the model. So, if your end goal is trying to a smooth curve around all this, sparse data, there are technology you can use. Interpolation, smoothing, wavelet transform, Fourier transform, a lot of techniques, you can do it. But if your end goal is trying to use this data to do further analysis, then you are in a position that you have to justify the newly implemented data, how that impact your overall model uncertainty. So like Giuseppe mentioned, it's a bigger topic, but the underlying idea is you building a model. And when you build a model, you have to define a model. That's the way I'm saying.
Thanks, Longzhu. Thanks, Giuseppe. Do we have any other questions? We have like a few minutes more, maybe. Then if not, I would like to thank Giuseppe and Longzhu for this very interesting talk. I think many of the, in particular for students not from computer science or not having so many like coding experience, I think this would be quite like adding to them. So a lot of the tools that you and research you have talked about maybe quite adding to them. So I think if there are more and more chances for people to be exposed to this more, so they would be more like familiar with this. And we hope we can have the opportunity to like introduce your whole courses to China, to like universities like Beijing Normal University. And I have been using Giuseppe and Longzhu's tools for like only maybe 10%, but it's already very helpful to me. So it's already like improved like the research that I'm doing now. So I hope we can have more chances, more opportunities to learn from you. So very interesting talk. Thank you very much. We will follow up maybe later. And also if you have more questions, you can direct to Giuseppe and Longzhu or even me. I can make a connection between you perhaps. So thank you very much. So we will end today.
Yeah, thank you very much for your attention.
Yeah.
Yeah, thank you, Shadow.
Thank you.